Hello everyone. Today I was initially planning to cover the problems of the Google Code Jam 2021 finals, but I noticed that the Google YouTube channel has actually uploaded explanations of all the problems. So instead I'll be going over a spicy number theory lemma known as the lifting the exponent lemma. So this lemma I think is actually quite an obscure lemma and I haven't really seen it being used in any of the contests that I took part when I was in high school. But recently it has appeared in the AIME 2020, and more surprisingly, it has even appeared in the Google Kickstart problem of this year. So without further ado, let's take a look at what this lemma is about. So before going to into the lemma, we need to define a function. So let P be a prime. So we define a function known as the periodic valuation, and this function is defined on the integers. So basically, you put in the integer, and what it spits out is what is the maximum power of the prime that divides the integer. So if the prime doesn't divide the integer, the maximum power is 0. If p squared divides the integer but p cubed doesn't, then the maximum power is 2. If n equals to 0, we just define it to be infinity. So this is the periodic valuation function. Now comes the lemma. So let x and y be integers and let p be a prime such that p divides x minus y, but p doesn't divide x nor p divides y. Okay, so the whole point of the lemma is to figure out what is the highest power of the prime that divides x to the n minus y to the n, where n is a positive integer. So normally, x to the n is a big number, y to the n is a big number. It's very hard to tell what is the largest prime that divides it. But with this lemma, this expression is actually equal to just v of x minus y plus v of n. So x minus y very easy to evaluate, n very easy to evaluate. So complicated expression here is simplified into sum of two simple numbers. Now the only exception to the formula is that if p equals 2 and n is even, then actually the formula is the same as before, but you need to add on v of x plus y minus 1. Okay, so I won't go over the proof of this. A proof can be found in the Wikipedia article, for example. Instead, I'll be showing you how this lemma was applied to the AIME problem as well as the Google Kickstart problem. So for the AIME problem, we have the following question. So let n be the least integer for which 149 to the power n minus 2 to the power n is divisible by 3 cubed times 5 to the power 5 times 7 to the power 7. We're supposed to find the number of positive integer divisors of n. Okay, so basically you're supposed to find out what n is. So let's see firstly what is needed to have 3 cubed divides this. So this expression here, you can separately consider 3 cubed dividing this, then 5 to the power 5 dividing this, and 7 to the power 7 dividing this to break the problem up into parts. So starting first with the 3 cubed part. Okay, so we can let p be the prime 3, and in this case we can apply the LTE lemma, and this expression obviously is screaming to you to use the LTE lemma. So we can use the LTE lemma because 3 divides the x minus y, so 149 minus 2, but 3 doesn't divide x nor 3 divides y. So if you use the LTE lemma, you have that v of that gigantic expression is actually just v of 147 plus v of n. And v of 147 in this case is equal to 1. So in order for this thing to be at least 3, v of n must be at least 2. So in other words, in order to have 3 cubed dividing this thing, this is equivalent to having 3 square dividing n. So you can see where this is going. Is actually the problem becomes much simpler once you know that you are supposed to apply the LTE lemma. On the other hand, if you don't know the LTE lemma, you're probably stuck. Okay, let's continue on. Now we do the case p equals 7. We'll keep the case p equals 5 later on because it's more complicated. Okay, so let p equals 7. Again, we can apply the LTE lemma because 7 divides x minus y, but 7 doesn't divide x and 7 doesn't divide y. So it's valid to apply LTE lemma, which tells us that v of the big thing equals to v of 147 plus v of n. This time v of 147 is 2 because 49 divides it. So same thing for the left side to be at least 7. V of n must be at least 5. So we conclude that for 7 to the power 7 to divide this thing is the same as 7 to the power of 5 dividing n. Okay, very good. How about the case p equals 5? Well, in the first case, you realize that you can't just directly apply LT because 149 minus 2 is not divisible by 5. But this spells a bigger problem. If the x and y are not even congruent mod 5, then we need to first check what is the condition we need to have on n, so that at this first we have 5 dividing 149 to the power n minus 2 to the power n before we even talk about 5 to the power of 5. Okay, so let's investigate this first. Now 149 to the power n modulo 5 follows the pattern 41 41 41 41 and so on, whereas 2 to the power n follows the pattern 2431 2431 and so on. Okay, so this tells us that for us to even first have 5 dividing the expression, we need n to be a multiple of 4, so that we have 1 minus 1. Okay, so now we know first that n is equal to 4k, so we can consider the requirement 5 to the power of 5 dividing the expression, but we now sub in n equals 4k, so we can write it in this form. So the two requirements are identical, but this time the advantage is that we can apply the LTE lemma because k is now the power, the x is the 149 to the power of 4, and y is the 2 to the power of 4. So in this case, 5 divides x minus y by construction, because we investigated that when n equals 4, you have 1 minus 1, right? Okay, but then 5 doesn't divide this, and 5 doesn't divide this. So when we apply the LT lemma, we have this ugly expression. It's basically just v of x minus y plus v of n. And so let us investigate what is this value. It's actually not hard to evaluate once you have a concrete number here. But the quickest way is to see that 149 is congruent to minus 1 mod 25. So you have this thing is congruent minus 1 to the power of 4, minus 16 is congruent to 10 mod 25. So this thing is not divisible by 25. So v of the expression is equal to 1. So this is 1. In order for the left side to be at least 5, v of n must be at least 4. So oh yes, this is supposed to be k, sorry about that. So this is v of k. And at the same time, remember that n equals 4k. So the requirement is equivalent to 4 times 5 to the power of 4 is it divides n. Okay, so putting everything together, we see that the minimum n must have 2 square, 3 square, 5 to the power of 4, and 7 to the power of 5, and that gives us 270 positive divisors. So that's all to this problem 12, and so far I only know LT as the only solution to this problem, and with LT is a big machine gun that really helps you solve the problem directly. And this is where we move on to the Google Kickstart problem. Now before going there, I need to first go through a quick review of segment trees because it will be heavily used in that problem. So for those who are less familiar, segment trees basically allow us to perform query on segments of an array. So for example, if you have an array of elements here, you could ask things like what is the sum of elements from this point to this point. So add all this up. Or what is the sum of elements from this point to this point, for example. So I'll focus on sum, but it can be used for other things like maximum, minimum, and so on. Okay, so of course, the naive way is each time you receive a query, you just add up the elements directly. But that requires about linear time, so order of n time in the worst case. So there's a smarter way to do this, which is to store certain pre-computed values. So for example, basically this red dot is the sum of these two blue, this red is the sum of these two blue, and then this red is the sum of these two red, so it's actually the sum of these 4 blues. Then this red also sum of these two, this red sum of these two, this red sum of these two red. So this red I pre-compute a sum of these two red, and this red will be the sum of these 8 red blues. So if I receive a query, let's say sum from here to here, the way I do it is I pull out values from rate where I can do so. So I can just take the sum of this plus this rate plus this rate, and that will give me the sum of these 7 values here. So I only need to add up a log n number of terms each time I have a query instead of order n number of terms. So that is a great improvement for each query. So of course you may ask, well, then why not I just pre-compute all possible sums of all possible segments? Well, the thing is that what happens if you have an update? So that works for a static array, but then if let's say I'm updating elements sometimes also, then I'll have to pre-compute all the segments that it overlaps with the element that has changed, and that is not very efficient. So a segment tree actually balances these two requirements of update and query at the same time. So why is update efficient? Well, if I update this element, I only need to bubble upwards and update these red elements that are the ancestors of the blue. So I only need to update a log n number of elements. So updates and queries are both log n, which makes this a very neat data structure for such purposes. Okay, so enough on segment trees. Now we go to the Google Kickstart Round D problem 4. So this is actually a monster problem. It's the last problem of the Kickstart round, and the success rate, it was extremely low, and I think only 30 participants got full score on this problem during the contest, which is a very small fraction. Okay, so for this problem, you are given a prime p. They define Vx to be the degree of p in the prime factorization of x. So basically, V is the same as the p-adic valuation function that we defined earlier. But for this specific problem, they have defined V of 0 to be 0. Okay, now you are given an array with n elements, and you need to process two types of queries. There are Q queries, they are of two types. The first type is an update query. So they tell you it's type 1 for update query. They give you a position and a value. You are supposed to assign the value to that given position. Okay, then type 2 is a query. So they tell you it's type 2 for a actual query. S will be used in the query, then L and R, so from left to right. So we are supposed to print this expression sum up from the left to the right segment of the array. And what is this expression is A, the element to the S minus the element mod P to the S. So it's an ugly looking expression, but you can very quickly tell that using LTE lemma is going to really save your life here. So before going to the actual solution, I think it's important to look at the input, output, and limits as a group CP candidate. So let us see what's the input. So the first line will give you the number of test cases T test cases follow. Each line of the first line of each test case starts with 3 positive integers NQP. So basically the number of elements in the array, the number of queries you're going to have, and the prime number P. So notice that the prime number P is going to be fixed for the whole test case. Okay, and then the next line contains the array A1 to AN, and then after that it will be the Q query, so either type 1 or type 2 queries. And then you're supposed to output a line containing the case number followed by a list of the answers for each query of type 2. So what is the query answer? You stack them together and output it. Okay, and then here are the limits. I won't go through in detail, but basically all the numbers can be quite big, so there's no chance of brute forcing. Okay, to give me space to go through the solution, I'm just going to retain this part of the problem statement to the rest should be quite memorable. So the way we'll do it is we'll actually, in the simplest way, in simplest case, you would wish that actually you can store all these values in a segment tree, and then you can just query your segment tree when you have a query, and then when you need to update, you just update your element in the segment tree. But that doesn't really work directly, because how do you compute this value? You want to use the LT lemma, and LT lemma works only when the prime doesn't divide x and doesn't divide y, correct? So you need to split into two cases. So we'll use two segment trees actually. Actually, we'll use more, but let's start off with two segment trees first. One segment tree will be used for when the prime divides the element, and the other will be when the prime doesn't divide element. So the way we'll do is as follows. You have the element in your array. If that is divisible by the prime, you store the value you want to calculate in the array, and in the other segment tree you store the value 0. On the other hand, if your element is not divisible by p, you store the value you want in the segment tree, and then in the first segment tree you store 0. And then notice also that in this special case, right, when the element is smaller than p, actually the AI here and the AI mod p will be the same numerical number, so the expression in the bracket is actually 0. So we are going to get v of 0, which is 0. So if AI is actually smaller than p, which is a third special case, I'm going to just set both of these values in the segment tree to be 0. So that now if I face with a query from L to R, right, I'll basically query from L to R in the first segment tree and the second segment tree and add the answers up. And then that will give me the final answer. So this is the rough frame of how it works. Of course, if I have a update query, then I just update the values in the first and second segment tree respectively. Okay, but then I cannot actually directly compute the answer that I want and store in the segment trees, because S varies from one query to another. So actually this is what makes it complicated. Now let's look at this case first. How do I store the answer that I want in the segment tree? Now the value that I want, if AI is divisible by p, this part will be 0. So the value I want is v of AI to the power of s. And this is exactly the same as s times v of AI. So the clever thing to do now is to actually store v of AI. I can always compute this. I don't need s. S is something that is only given for each query, so it cannot be something that I store in the segment tree itself. So I store instead v of AI, and then when I have a query of type 2, I sum up from L to R, and I multiply that sum with the s that I'm given in that query. So this piece will give me the sum of all the elements here where AI is divisible by p. Okay, then how about this side? How do I store the values? Okay, if AI is not divisible by p, let's assume first that p is not equal to 2, so I don't have to take care of the exception case in the LTE lemma. So this value here is the x to the s minus y to the s, right? So it's x minus y plus v of s. So it's actually this expression here. And so I see that, okay, the first piece, well, I can always store this first piece in my segment tree, and then when I need to sum up for a given query, I can just query directly on the segment tree and sum up all the pieces that are given by this. How about the vs? This is tricky. I cannot store vs in a segment tree because I cannot store s. S depends varies from query to query. But then I can store the value 1 instead in the segment tree. And then when I need to sum up vs across in a query, I just query in this segment tree, and then I multiply the whole thing by vs. And vs can be computed in log s time. Basically, I just take s and keep dividing by p until it's no longer divisible. So for this, actually I need two segment trees for this case. I separately update each segment tree every time I have a update query, and then when I have an actual query, I use the segment tree here, I add up, I also add this, and I get everything solved for the case where p is not equal to 2. Now when p equals to 2, actually when you get a type 2 query, you can check, is s odd? If s is odd, right, we haven't hit the exception case yet. We can continue to just query our 3 segment trees, and we add up and we get the answer. However, when S is even, and here P equals 2, the expression that is in the summand is actually what we have before plus the additional term V of x minus y minus 1. So how do we address this? Well, we create yet another segment tree that stores the, this should be V of x plus y. So once again, create another segment tree and store the value of V of x plus y minus 1. And then when I need to query to return a query, I call the query on this segment tree and get the value. So when I get a query, I check is S even. If so, I need to actually add up 4 different queries from 4 segment trees. So that is all from this problem. It's actually very difficult problem as expected for last question of a Kickstart problem. But actually with the LTE lemma, and given that is a segment type of query, it's very natural to consider segment trees. So when you think you want to use LTE lemma plus you want to use segment trees, actually you are almost like 90% of the way to the solution, and after that it's actually not a very difficult problem to finish up. So hope you enjoy this video. It's a bit of a special video that covers both competition math and competitive programming. So stay tuned, subscribe to the channel, and see you soon.